Multivariable calculus, we're back in section 15.5, our first day. The video left off, we had just begun looking at example 2. We're finding the mass of this triangular lamina. You can see we're pretty much good to go. You can see that this region, this mass right here that we're going to be finding is a type 1 double integral. And as we work this out, then it's going to be something that we can do quickly. We can see that as we draw this vertical bar, our y boundaries are going to go from the x-axis, which is 0. Up here we've got y equals negative 2x plus 2. And we're going to take all such vertical bars from x equals 0 to x equals 1. Now, for the sake of time, these problems can get rather long. What you're going to be able to do is to use your 89 very quickly just to evaluate this. And whether you're doing it by hand or working it out this way, you're good to go. So, we found the mass right here. If we wanted to find the moment about the x-axis, you can remember that would be the average distance on this lamina from the x-axis. That would be a y here, and we'd have 1 plus 3x plus y, and we'd have our d and dA right here. But this integral can be worked out as a type 1 integral, just as we had done previously. And like we had just done as we were working this double integral out, we most certainly may use the 89 to speed this up. I've already worked it out. You can quickly confirm that the moment about the x-axis would be 11 over 6. And then likewise, the moment about the y-axis, well, you can see then we'd have an x. You can see whatever we have for a subscript here, it changes. It's a nice way as many kids will think about that. You can pretty much see it's going to be the exact basic scenario here. It's still a type 1 region as we're working this out. And again, allowing the TI-89 to help us do this quickly is a wonderful tool. You can see that you should get a value of 1. Now, as we're finding the center of mass, x bar, of course, is going to be the moment about the y-axis all over the mass. And ultimately, what that's going to involve is you see this, and this is in yellow. You've got your y right here, but I always remember it in this regard. The x bar is going to really have that x times the density function inside. So we already found what my was. That was going to be a 1 all over this 8/3. That's the reciprocal. That should just be 3/8. Likewise, the center of mass's y-coordinate would be the moment about the x-axis, and that would be 11 over 6 divided by 8/3. Well, that's 11 over 6 times 3/8, and 3 goes into 6 twice, so we'd get 11 over 16. So the center of mass, of course, is a point, and it's going to be this point, 11 over 16, comma 3 over 8. All right, one more example, and this one is a little bit more abstract. We're not given an exact density function. We're going to have to write it out. It says the density at any point on a semicircular lamina is proportional, which means there's some constant, like k times, the distance from, let's change this here, the center of the circle. And the circle is given to us very abstractly. It's just given a center of 0, 0. some abstract radius of a, non-specified. So a could be any real number. It could be, well, I should say a positive real number. And, with that in mind, we're going to have a semicircle above the x-axis. So in yellow, we have that depicted. If we were to pick some arbitrary point on the lamina right here, x comma y, obviously there would be a distance to the center, and that would be right here. And as we could work this out, I hope you can see we could build a right triangle. This would be an x and a y, and we could talk about that distance. With the Pythagorean theorem, it would only take a moment to see d squared equals x squared plus y squared. And distance is going to be a non-negative value, so we don't have to take a negative square root here. But d is going to be that radical x squared plus y squared. So the density, if we look at rho right here, we've got x comma y. It's proportional, so there's k times that distance. Well, what is that distance? That distance is going to be radical x squared plus y squared. So we're only going to find the mass of this lamina, and that's going to shorten up our problem a little bit. Well, the mass is going to be this double integral over some region D, which we've highlighted in yellow. And we've got our density function right here. And it's only going to take us a moment then to see that, well, that's k times the square root of x squared plus y squared. However, when we're working with circular regions, like we are right here, of course, we could most definitely jump in and realize that polars can come and help us. As we jump back to polars, you might remember that converting from rectangular to polar, we always said, look, if you had an x comma y, we'd always have x squared plus y squared would equal r squared, as we'd be on a curve. We knew that x was equal to r cosine of theta, y was equal to r sine of theta. Perhaps we don't even need that. And we also had the tangent of theta as we were looking at just some arbitrary relationship here. Here's your theta. We'd know tangent of theta would be y over x in case we ever needed that. But I guess what we're really seeing right here, without a doubt, is that there is a link. We can say x squared plus y squared is r squared. Well, here's your x squared plus y squared right in here. And you can say, well, that's the square root of r squared if we're going to convert. So that's going to just be an r. Or we could even solve for r right here and see it's the square root of x squared plus y squared. But remember, dA is going to go to r dr d theta. And then we can say, well, what about your r boundaries? Well, as you're looking at this yellow lamina right here, your radius, remember, it's everything inside. Your radius is going to go from 0 as far to a. And our angle boundaries, well, we don't have a full circle. We're only going to go between 0 and pi. So cleaning this up, we'll have kr squared dr d theta. And let's go ahead and finish this quickly. We'll first just look at this integral right here. We'll take our antiderivative. We'll get r cubed all over 3 evaluated between 0 and a. We'll work with this outside part in just a moment. Finishing up with our fundamental theorem, you can say that we can keep k over 3 outside, and we'll have a to the third minus 0. And, it's not going to be too bad right now. You can see we're going to be left with a k a cubed all over 3. And now we just have to integrate here with respect to theta. So we'll have a k a cubed all over 3 theta evaluating between pi and 0, well, I think you can see very quickly what is going to happen. Your mass is just going to be Ka cubed pi all over 3. And we are done.